And those are found, that the set is found. Let's kind of look at this. If I take my two diagonals, let's just, let me clean this up. I'm going to cut and paste it real quick so we can blow it up a little bit. If we look at those two, I'm going to draw one diagonal from A to C. Let's look at that red diagonal. And then we'll do one from B to D. So that one, let's change that color to, well, maybe I won't. All right. I don't know how well you guys can tell, but that's a blue segment there. And let's say it goes from B to D. Would you agree that when I look at the red one, the two triangles that are created there are incongruent triangles? Or let me rephrase it. They are congruent triangles, but they're non-isosceles. Would you agree with that? They're non-isosceles. Okay. The congruent angles that we deal with in this theorem, this set of opposite angles that are congruent, they exist. Let's put this in parentheses. They exist within the non-isosceles triangles created by a diagonal. Okay. When you take your diagonals and look at them either individually or together, if I look at them individually like I've got them put together here in these two kites, look at the bottom set. Okay. Would you agree that in that bottom set of triangles, they are both isosceles triangles? Does that make sense? They are incongruent isosceles triangles, where up top, these would have been congruent non-isosceles, right? Okay, so maybe that's something we even put on here. We write here that they should be congruent non-isosceles triangles created by a diagonal. But your congruent angles will exist inside those triangles. Okay, here you're not going to get, with these two triangles, you're not going to get any congruencies there with angles. A lot of people want to make the argument that angle A and angle C are always the same, okay, or they look the same. The more rhomboidal that is, the closer C is to A, those two angles start to become the same. Does that make sense? But the further I pull C away from A, okay, the smaller angle C becomes, and A stays obviously what it is. So those two angles are not congruent, but B and D are. Okay. When I put both diagonals in, does it look like that red one bisects BD? Does that make sense? Okay. So I'm going to write another theorem down here that one diagonal and it'll always be the one that separates the two isosceles triangles will be bisected by the other diagonal. also going to write this bisection is not reciprocating or reciprocal. If let's say Hunter throws a punch at me and I reciprocate, what does that mean? I hit him back, right? Okay. So when something gets bisected, okay, and it reciprocates, that means it bisects something else, right? Okay. So we've seen some situations where we have two segments, and this happens with parallelograms. We have two diagonals that bisect each other, right? That's a reciprocating behavior. Diagonal 1 bisects diagonal 2, and diagonal 2 bisects diagonal 1. Okay? With kites, that reciprocating feature does not happen. Only one diagonal gets bisected, and the other one does not. Okay, is that okay with everybody? All right. If they did, it would make it a parallelogram and no longer a kite. Okay. The next theorem is that one diagonal, and it is the one that separates the congruent non-isosceles triangles. So in this case, it would be the one that is actually bisecting the other one, okay, will bisect one set of opposite angles. And that one set of opposite angles are the I'll write this way, the incongruent set of opposite angles. So we're getting at there, and I'll go back to that in a minute. And we're getting at there is that this red diagonal here, would you agree that's the diagonal that is separating the two non-isosceles triangles? Let's top one from A, B, C, and this bottom one, A, D, C. Or it's the one that is bisecting the other diagonal. However you want to refer to this red diagonal, okay? It is bisecting the opposite angles that are incongruent. If I look at angle A and angle C, we talked about angle A and angle C being incongruent, right? When I draw that diagonal, that red diagonal in here, that red diagonal is making that angle congruent to that one, and this one congruent to that one. It's bisecting those incongruent angles of angle A and angle C for my kite. Does that make sense? Okay, it's a lot of, when we dealt with parallelograms, we could always say, oh, well, both sets of opposite angles got cut in half or something like that. Especially when we talk about rhombuses. With rhombuses, we would say both sets of opposite angles got bisected, okay? Here, it's only one set, so we have to have some defining feature that allows us to always accurately and adequately find that one set that gets bisected, okay? You can think of it, if we look at this set of triangles down here, you can think about angle A as the vertex angle of that isosceles triangle on the left, and angle C as the vertex angle of the isosceles triangle on the right. Those vertex angles of the isosceles triangles are the ones that get bisected. Okay? A lot of different ways we can verbalize this, a lot of different ways we can relate the diagonal to parts of these triangles or the diagonals to parts of these kites. But what we need to understand is that one set of angles gets bisected, the other side does not. Okay? And it ultimately is dictated by this point that we drag away from our rhombus. Does that make sense? Okay, so when I go back to this image here, when I drag that point away from my rhombus that I started with, now my hopes are you can see, well, A and C, those angles are going to be congruent, right? Okay. The diagonal DB is going to bisect angle D and angle B. Okay. Hopefully, if you throw in AC there, you can see that doesn't bisect angle A or angle C. We can also see that vertical diagonal DB is going to cut the horizontal diagonal AC in half. It's going to bisect AC. Okay. All that changes the moment I look at this and pull that one that way. Now angle A and angle C are going to get bisected. Angle D and angle B are congruent. DB will get bisected by AC. We just got to be able to locate those. Okay? And hopefully these theorems and how we stated these theorems allow us to do that adequately. Okay. Is that all right? So those are your 4 theorems that we deal with for a kite. Like I said, your textbook only shows one of those, which I think is kind of misleading because you're going to need those other facts as well as we move through kind of finishing that 6.6 assignment. So you're going to see in your homework a question. I think I've got it. I got to cut and paste it from this side. There it is. So they gave you a couple questions that looked like this and asked you to solve for X and Y. Now, they do this on purpose. They make it look like a kite, but it's a kite that looks very similar to a rhombus. Would you guys agree with that? Okay. So when I look at, like I'm just going to go to GeoGebra real quick again. If I look at this right here, that's my rhombus. Okay. Like your homework question does like that. Like they just move it just a slight bit. Okay. And they're doing that on purpose. They're wanting to try to get you to make a mistake with this stuff. Okay. What we need to understand to do that problem is that no matter what I'm looking at, if it is a kite, none of my segments will be parallel. Does that make sense? Okay. And that's what they're trying to get you to, and on this question I think it's solving for Y. They try to make you make a mistake by saying that Y and 2Y minus 15 are congruent. Okay? Because they look like it, right? Okay, if I look at that image right there, okay? It looks like I've got a line here, a line there, cut by a transversal, and they're trying to get you to say, well, Y has got to be equal to 2Y minus 15. Well, think about that. If I were to do that, if I were to say Y is equal to 2Y minus 15, that is going to make that top green line that I highlighted and the bottom green line that I highlighted, it's going to make them parallel. Does that make sense? And if those are parallel, then this thing is a trapezoid and not a kite. Does that make sense to everybody? Okay. So we have to be on the lookout for that. Just be careful that the way they distort their images or draw them, they intentionally do that to get you to make mistakes. Okay. If this is a kite, what do you know about that angle there in comparison to that angle there? They're the same. Okay. Those were the opposite angles, one set of opposite angles that have to be congruent, and they belong, okay, in the non-isosceles triangles. Your congruent angles are always part of your non-isosceles triangles, okay? So we're kind of missing this dotted diagonal there, but for this particular problem, we don't need that anyways. So what are you going to say if they're congruent? You're going to say that those two things are equal, right? So we'll say 2x plus 5 equals 3x minus 45. So I give you 50 for your x. Does that make sense? Add 45, subtract 2x. Okay, so that's great. We now know that. Now the next question is solve for y. And that's where most people make the mistake, is they say, well, y's got to equal 2y minus 15. Okay? But we have to use a fact that we've used an endless amount of times throughout the year. Okay? If I know that this is x is 50, doesn't this angle right here have to be 105 degrees? Now I want to look at this diagonal. Now this diagonal here, this horizontal diagonal they have there, that is the diagonal, okay, that is splitting my knot into two non-isosceles triangles. That diagonal, maybe you think about it as the diagonal that is opposite your congruent angles of your kite. Does that make sense? If the top and bottom angles are congruent, would you agree that diagonal is kind of opposite them or sandwiched between them? Does that make sense? You visualize that? Okay. That diagonal is going to be the diagonal that bisects opposite angles. Okay? So it bisects opposite angles. But what I want you guys to understand is that that angle there and that angle there are not the same. And that's what they're trying to get you to think about when we're looking at this. They're trying to get you to use your, let your eyes play tricks on you, and to get you guys to revert to something you're comfortable with and saying that that y has got to be the same as that angle right there. But the argument is, when it looks like something like this, my hopes are you see that angle A here is not the same thing as angle C, right? So when I split those with that segment there, and I'll make it, we'll just zoom in on this a little bit. So this angle here where my cursor is ends up being, looks like it's going to be 45 degrees, but I'll do it this way. That angle of 45 degrees is obviously not the same thing as that angle there, which they're saying is 9.46. Does that make sense to everybody? Okay. The only time that those are the same is when we do this. The only way I can get those two things to be the same is that. And now if I were to look at the segment lengths here, they're all the same, so it's a rhombus now, right? Does that make sense to everybody? Okay. So these two angles are not the same. So we have an issue here. How do I adjust this so I can solve for y? And it's something that we've used a lot, and sometimes we overlook it because it's kind of a simple procedure. What should those three angles add up to? 180, right? Do you have two of them? You have 2y minus 15, right? Plus this green one at the bottom, which is 105. Now you need this other one. Do you know this angle right here? Do you know this black one that I shaded in? What's that got to be? It's got to be y, right? Doesn't this diagonal here split the incongruent opposite angles? Splits them in half. So this angle right here has to be y as well. So now if I look at that triangle, I've got plus y here. This stuff should all add up to 180. So we're going to use that triangle angle sum theorem to help us out solving for y. I think y, when you go through all that math, y ends up being 30. Does that kind of make sense? Okay. I want to show you guys. So I think some people were having issues with that question, and the main thing I was seeing is that they were equating those two things. So make sure you don't do that, because when you do that, you then change that from a kite to a rhombus. I've shown you this thing many times, probably 3 or 4 times already. I want you guys to now write it. Okay. And what is nice about this is we call this a flow chart. Okay. But what we're really going to do is a lot of times flow charts, you start at the top and you just filter your way down. But this one's going to, I think the best way to kind of view it and use it is maybe to go from the bottom up. Okay. When we look at our polygons, okay, one of our our task with polygons is to first classify, you know, how many sides does it have, and if it ends up with 4 sides, we end up classifying it as a quadrilateral, right? But that quadrilateral then can be broken down into 3 subgroups. And what's nice about the way those 3 subgroups kind of work themselves out is, by definition, essentially tells us that those 3 subgroups of quadrilaterals are developed by looking at the number of parallel sides. Okay? So if I have my quadrilateral, if I have no parallel sides, it's a kite. Okay? So if I'm in the coordinate plane and I want to know, classify this thing as a kite, a trapezoid, or a parallelogram, the discriminating feature is slopes, right? Does that make sense? So no matter what category I want to be in here, I've got to figure out slopes. So if I've got 4 points, and I find all 4 slopes, I should be able to quickly tell, are none of them equal? Because if none of them are equal, then it could be a kite, or it might just be a general quadrilateral. Are only one pair of slopes equal? Because then it's going to be a trapezoid. Are both pairs of opposite sides parallel? Then it's going to be a parallelogram. Okay? But one thing you got to make sure of, if you do get to the point where you are in the coordinate plane, and we'll do this a little bit tomorrow, and you see that none of the slopes are the same, you can't automatically say it's a kite. Does that make sense? Because you have to determine, well, if none of the sides are parallel, it could actually be this shape here. So the way this flow chart is set up is actually those blue shapes actually represent quadrilaterals or a kite or a trapezoid, right? Those shapes are accurate to the names that are in them. Just because you have no parallel sides doesn't automatically mean it's a kite. You need to go find distances to differentiate that. Okay. But once I've got an idea of whether it's going to be a kite, a trapezoid, or a parallelogram, the defining features are then talking about distances. Okay? So if I have no pairs of parallel sides, and I want to determine kite or quadrilateral, I'm going to go find distances, right? Find all 4 side lengths. If there's a relationship that allows me to say it's a kite, then great. If there's no relationship, then it defaults to a quadrilateral. That's awesome. Okay? If I'm working with the quadrilateral, I found the slopes, and I found one set of sides to be parallel. One set of sides to be parallel. And I want to determine, okay, is it just a trapezoid or is it an isosceles trapezoid? Well, in order to make that differentiation, I need to talk about distances again. Okay? So I got my slopes, and then I'm going to look at distances. I'm going to be looking at distances of the sides that are not parallel. Because to be an isosceles trapezoid, the legs, the non-parallel sides, have to be congruent. Okay? So far, in looking at kind of this cluster of shapes, in order to classify that cluster, I need slope, and then I'm going to just jump straight into talking about distances, right? And what we've talked about in the past is once you have the slopes, you have all the arithmetic for finding the distance. So that should be kind of an easy jump from slope to distance. Okay? Once you determine whether it's a parallelogram, you got 2 pairs of parallel sides, then we start doing all the work that we talked about last week on Wednesday and Thursday and Friday. Of saying, okay, well, it's a parallelogram. Let's see, is it a rectangle? Does it have one right angle? And that should be nice because I should already have the slopes built, right? I should be able to find right angles off those slopes. And then the question will be, okay, well, if is it a rectangle and is it also a rhombus? And that'll be nice because if it's a rhombus, I've already got the slopes. If I use those slopes accordingly, I can find the rhombus's distances or lengths. Okay? And if I'm able to show that a shape is both a rectangle and a rhombus, then I'll automatically call it a square. Okay? So hopefully that flow chart and understanding your slope formula and your distance formula, okay, can help you kind of classify a shape effectively, quickly. Okay? If you remember at the beginning of the chapter, I told you there's going to be a lot of properties for like a square. Square is going to have all the properties that the rectangle has. It's going to have all the properties the rhombus has all the properties of parallelogram, have all the properties of quadrilateral, have all the properties of polygon, so forth. Okay? I'm going to ask you what those properties are. Okay? I'm going to say, here's a square. Check off all the properties you know exist for a square. Here's an isosceles trapezoid. Check off all the properties that you know for an isosceles trapezoid. Okay, and here's the way that I think is important for you to structure the way you think about things. If I'm interested in just maybe a rhombus, let's say that's the block that I'm in. I'll say find out or give me all the properties of a rhombus. Okay, so here's the thing. I've got to know a couple things that make a rhombus special. But then can't I automatically click off the things that are the shape that are one level or one tier above it? Isn't a rhombus going to be a parallelogram? Does that make sense? Okay. So once I know what all the properties that make a rhombus special, I'm then going to go and click all the properties that make a rhombus a parallelogram. Okay, or all the properties that are true for a parallelogram. And then I'm going to go click off all the properties that are true for a quadrilateral. And then maybe any properties that exist that I know for a polygon. So what I'm trying to get at here, you hear the questions, is a rectangle a square or is a square a rectangle? We can answer those questions using this flow chart from the bottom up, just like I did there. What I would suggest doing, like let's just do an easy one, is an isosceles trapezoid a trapezoid. What you do is you take that first object that I gave you, isosceles trapezoid, and you put yourself at that position. And now by only moving upward, can you get to trapezoid? If I move up in that flow chart, do I get to trapezoid? Does that make sense? So the answer is yes, an isosceles trapezoid is a trapezoid. Now let me phrase it this way. Let's reverse it. Is a trapezoid, so you're putting yourself here, is a trapezoid an isosceles trapezoid? Can I, by moving upward in this flow chart, can I get myself to the isosceles trapezoid category? No, right? So a trapezoid is not an isosceles trapezoid. So here's the question. Is a rectangle a square? Can you get from rectangle to square by moving upward? No. Okay. Is a rectangle a parallelogram? Yeah, because I can start a rectangle, move upward, get the parallelogram, right? So all these subgroups are classified first as the group or the tier that is above them. So a rectangle is not a square, but is a square a rectangle? Should be, because I can move upward to it, right? Okay. So knowing that flow chart, knowing that picture, kind of a graphical organizer, can help you answer those types of questions. Okay. I'm going to give you a shape. I'm going to say square. I'm going to ask you to go through, not only mark the properties, but then maybe the next question says, mark all of the shapes that a square is classified as. Well, a square is a rectangle. We check rectangle off. A square is also a rhombus. We check rhombus off. A square is also a parallelogram. We check that off. A square is a quadrilateral. We check that off. It's a polygon. Check that off. Does that make sense? Okay. So I think that's going to be useful for us. It's also, I think, something that could be useful in the coordinate geometry when we're trying to identify something. I'll give you a quadrilateral tomorrow, and I'm going to say, best classify this. Give you 4 points and have at it. Okay, determine. I'm not going to direct you. Prove that this is a kite or prove that's a square, something like that. We'll say it's quadrilateral. Best classify it. Okay, and you're going to have to be able to understand this flow chart to be able to do that. Okay, first thing you're going to do is determine parallel sides. If you got any of those, and that'll get the ball rolling, and then you can go from there. Okay, so that's kind of what we'll do tomorrow at the beginning of class. You should be able to finish up 6.6 now. That is open until tomorrow evening. I know it didn't shut off. Maybe it shut off last night. I don't know. But it is open until tomorrow evening. You should be able to finish that handful of kite questions. I don't think there were too many on there. From our Thursday tests, we'll probably do the retake on Tuesday of the following week.